Welcome to part 3 of my video playlist about the best methods for acylating amines. This presentation is about the preparation of amides from carboxylic acids, amines and some coupling or activating reagent. Because most carboxylic acids are stable and can be stored indefinitely, while acylating reagents may hydrolyze, chemists often feel more comfortable when activating a given carboxylic acid themselves, just before or during the acylation reaction. This can be done in a number of ways, and here I'll show you some examples of the most practical strategies. In situ activation of carboxylic acids can be done either with reagents that would also react irreversibly with amines and with reagents that react with carboxylate anions faster than with amines. In the former case, the acid must be activated first and the amine must be added afterwards. But when using coupling reagents that react faster with carboxylates than with amines, these reagents can be added to a mixture of acid and amine. The mechanism of such a coupling is shown here. The ammonium carboxylate would react with the coupling reagent to yield the activated acid and a new ammonium salt. The fraction of unprotonated amine can then be acylated by the activated acid. Sometimes a base must be added to increase the amount of free amine and thereby accelerate the reaction. Here's a selection of the most common activating reagents that are not compatible with amines. These can therefore only be used in a two-step sequence, where the acid is first activated and the amine is added afterwards. These include bulky acyl halides, such as pivaluryl chloride, that form mixed anhydrides with carboxylic acids, which mostly yield the expected amides upon reaction with amines. The steric bulk of the activating reagent prevents the formation of the wrong amide. Chloroformates and sulfonyl halides show a similar reactivity. Imidazolides can be readily prepared from carboxylic acids by mixing with carbonyl D-imidazole without any auxiliary base. In polar aprotic solvents, this reaction can be complete within minutes. Imidazolides are stable and can be isolated, but are usually used immediately. Cyanuric chloride can be used to convert carboxylic acids into acyl chlorides, but at low temperature, the initially formed mixed carboxylic cyanuric anhydride will be the acylating reagent. The most relevant coupling reagents compatible with amines are shown here. These include cationic reagents such as Ixtal fluor, phosphonium and uronium salts, which, because of their positive charge, react faster with anionic nucleophiles than with neutral ones. Then, most phosphorus-based electrophiles quickly form strong bonds with oxygen nucleophiles, but only weak bonds with nucleophilic nitrogen. Carbodiamides in combination with some auxiliary acid quickly convert carboxylic acids into active esters, even in the presence of primary or secondary amines. I'll show you the precise mechanism in a minute. Phosphonium salts react with carboxylates similar as in the Mitsunobu reaction. But instead of the carboxylate acting as nucleophile and being alkylated by an aliphatic alcohol, here the carboxylate acts as electrophile and acylates another oxygen nucleophile. The carboxylate first adds to the cationic phosphonium salt to yield a pentavalent phosphorus derivative, in which an intramolecular transfer of the other oxygen acid to the acyl group occurs. Uronium salts activate acids either by converting them into active esters or into O-acyl uronium salts, as shown here. The most common alcohol components in these coupling reagents are hydroxybenzotriazoles, but oximes or phenols can also be used. When compared to the use of isolated acylating reagents, in situ activation has the advantage of providing a higher degree of certainty about the quality of a given electrophile. Moreover, today a broad choice of activating reagents is available, covering a wide range of reactivities. In situ activation can often also be applied to carboxylic acids that contain functional groups incompatible with an electrophilic acyl group. One such example would be the protected multifunctional amino acids used in automated solid-phase peptide synthesis. Disadvantages include the high price of some of these reagents and that some of them generate a lot of waste. Then carbodiamides are allergenic and benzotriazoles explosive, but less dangerous alternatives have been found in recent years. Finally, the use of coupling reagents instead of isolated acylating reagents increases the number of parameters to be optimized and thereby the overall complexity and cost of optimization. The use of isolated acyl halides is discussed in the first part of this playlist, but acyl halides can also be generated just before the coupling with an amine, without the need of any isolation or even solvent change. Acyl fluorides, which are much less reactive than acyl chlorides, can be generated by treating carboxylic acids with sulfuryl fluoride or any of the deoxyfluorinating reagents developed in recent years. I discussed these reagents more thoroughly in my video about the conversion of aliphatic alcohols into alkyl fluorides. Acyl chlorides can be generated in situ by treatment of carboxylic acids with cyanuric chloride or with geminal dichlorides. Now I show you some specific examples of the use of activating reagents that are not compatible with amines and where the amine can only be added to the reaction mixture once the activation is complete. Thionyl chloride is the reagent of choice for the conversion of carboxylic acids into acyl chlorides, but this reaction often requires heating in the presence of catalytic amounts of an amide. It has been found, however, that a pre-activation of carboxylic acids with just a slight excess of thionyl chloride is possible in dimethylacetamide at -10 degrees Celsius. The structure of the resulting intermediate was not elucidated, but it could be a mixed sulfinic anhydride or an acyl iminium chloride. This intermediate reacts cleanly with amines to the corresponding amides, without the need of any additional base. This is an example of the formation and use of a mixed carboxylic sulfonic anhydride. This anhydride was sufficiently reactive to acylate toluidine at room temperature within 2 hours. As weak auxiliary base, methyl-imidazole was used. In this example, again a protected alpha amino acid anilide was prepared from a mixed anhydride. In this instance, pivalulyl chloride was the activating reagent and the weak auxiliary base N-methylmorpholine was used to enhance the reaction rate. Even substituted isobutyryl halides can be used as activating reagents, as shown here. The amine was in this case an unreactive N-methyl amino acid ester, but still a high yield of dipeptide was obtained. Mixed carbonic carboxylic anhydrides are less reactive than pure carboxylic anhydrides, but can still be used to prepare peptides in solution. Some mixed carbonic carboxylic anhydrides are not stable and quickly decarboxylate to esters. Therefore, these intermediates are usually prepared and used at a low temperature, as in this example. I'll show you some decarboxylations of these anhydrides at the end of this presentation. In this example, a sterically demanding acid was first converted into an imidazolide and then, upon reaction with ammonia, into an amide. Despite the use of a methanolic solution of ammonia, no methyl ester was formed, and the acylation was finished after only 1 hour at room temperature. This example is similar to the previous one, but here the unreactive 4-aminobenzonitrile was the nucleophile. In this case, the acylation was accelerated by heating to 80 degrees Celsius in the presence of 1 equivalent of dBu. Let's now have a look at some examples of amide formations with amine-compatible activating reagents. This is an older instance of the use of phosphorus oxychloride as coupling reagent. The yield wasn't high, but like in the thionyl chloride example earlier, such couplings may give higher yields in a more polar solvent and at lower temperature. In this more recent example, the authors obtained best results with the cyclic phosphonic anhydride T3P. Because of its high price and uncertainty about the patent situation, they opted, however, for diphenylphosphinic chloride instead, which also led to clean amide formation. Some of the side reactions observed here were displacement of bromide by chloride in the starting acid and decarbonylation, but these could be suppressed to acceptable levels when using the optimized coupling conditions shown here. The main problem of this example was racemization of the acid. A large number of different coupling strategies and bases were tested, and best results were obtained with the phosphonic anhydride and pyridine as base. Without base, no acylation of this unreactive aminopyridine occurred. Carbodiamides were among the first mild coupling reagents discovered and played an important role in the development of the synthesis of beta-lactam antibiotics and peptides in the 1950s and 60s. Carboxylic acids undergo a quick acid-catalyzed addition to carbodiamides, whereby an O-acyl isourea is formed. This intermediate is a moderately reactive acylating reagent, but can rearrange irreversibly to an N-acyl urea. This rearrangement can, however, be suppressed by an excess of acid, which will protonate the initially formed O-acyl isourea and thereby enhance its reactivity as acylating reagent. An excess of acid will of course also diminish the amount of free amine available, but usually higher yields and cleaner products are obtained when conducting these condensations in the presence of an excess of, for instance, hydroxybenzotriazole. If no amine is present, the O-acyl isourea will react with the starting acid and yield a symmetric anhydride, or with any alcohol or phenol present to yield esters. This is an organic synthesis example of the preparation of an amide with a carbodiamide alone, without any additional acid. Accordingly, the yield was not high and some N-acyl urea was probably also formed. Dicyclohexyl carbodiamide does not hydrolyze readily, but the resulting urea is difficult to remove by extraction. Therefore, other carbodiamides such as diisopropyl carbodiamide or the water-soluble ethyl dimethylaminopropyl carbodiamide are usually preferred. Here, for example, this water-soluble carbodiamide was used to facilitate the isolation of the product. The required dimethyl homoglutamate had been prepared in situ by heating homoglutamic acid in methanol with methane sulfonic acid, and the hopped ester was added directly to this mixture together with a small excess of triethylamine. Despite the complexity of the reaction mixture, the desired product was obtained in high yield. Like in the previous example, here the authors also prepared the active ester under acidic conditions prior to the addition of the amine, but this is not strictly necessary. Here an oxime ester was the electrophile. For the automated solid-phase synthesis of peptides, it is important that each coupling goes to completion, because otherwise complex product mixtures would result. Therefore, an excess of acylating reagent is usually used, and the synthesizers monitor the deprotection of the FMOC groups by UV to see if all couplings proceeded as expected and to identify positions where the coupling did not proceed as expected. Particularly difficult is, for instance, the acylation of N-methyl amino acids. In order to compare the effectiveness of three common uranium salt coupling reagents, chemists at Nova Biochem prepared a difficult pentapeptide and performed the difficult couplings for only 5 minutes. With uranium salts there is no danger of N-acyl urea formation, and the couplings were conducted under slightly basic conditions with an excess of D-pair. Only with HA2 the main product was indeed the target pentapeptide, while the other two coupling reagents gave large amounts of truncated peptides. For less difficult peptides and with longer coupling times, also TOTU or HBTU usually give good results. So, what are the most relevant potential side reactions? These are the same as those discussed in parts 1 and 2 of this playlist and depend on the reactivity of the intermediate acylating reagents and the precise reaction conditions. These include the acylation of other functional groups such as alcohols or thiols and the formation of nitriles. The stability of mixed carbonic carboxylic anhydrides depends a lot on their precise structure, but most undergo decarboxylation at room temperature or when heated. Here, for example, decarboxylation required 150 degrees Celsius, but could be catalyzed by a tertiary amine. More nucleophilic amines, such as DMAP, however, can bring about this decarboxylation already at 0 degrees Celsius. Then, some particularly strong acids can form mixed carbonic anhydrides that already decarboxylate at room temperature, as in this example. It is therefore advisable to keep mixed carbonic carboxylic anhydrides cold and not add any strong nucleophile other than the amine to be acylated. On this and the next slide there are some further examples which you can also find in the description of this video. The next presentation is about the use of carboxylic acids directly as acylating reagents, without any coupling reagent. These reactions usually require strong heating, but recently some new catalysts have been developed that allow these condensations to proceed already at room temperature. See you then!